Hello. Welcome back everyone to the session, and we are very pleased to have Virgile Guemard to tell us about lifts of quantum CSS codes. The mic.
Can you hear me? Okay. First of all, thanks to the organizers. And so yeah, this is about a generic construction to create some quantum LDPC code called the lift. And so we'll start by the very general observation that many recent CSS LDPC constructions use the process of lifting. And basically, this process just amounts to changing the entries of the parity check matrices from F2 to a larger ring. And this is really a recurrent step in many of the state-of-the-art constructions, such as the lifted product codes of Panteleev and Kalachov, or also the BB codes can be seen as doing this kind of process. But it's very difficult to lift a code in general and conserve the orthogonality of the parity check matrices. So we can ask the question, can we find other types of lifted CSS codes? And to do so we will take inspiration from linear codes, and there's an operation there called the lift of linear codes. And this operation is equivalent, at least in this talk, to a covering of the tanagraph of the code. And it's a very easy to implement operation and flexible. And it encapsulates many known codes, such that many constant weight codes. The Sipser-Spielmann codes can be seen, some of them can be seen as an example of this. And also its application into 5G new radio codes. So also the linear codes used in the lifted product, as I said, can be created by a lift in this sense. Okay, and so now we can ask the more specific question. So is there a lift procedure for CSS codes that generalizes the lift of linear codes? Okay, and so we'll start by just looking more closely at the lift of linear codes and then its extension to CSS codes. And then we'll talk about some new code constructions using the lift. Okay, so let's begin. In this talk, a code is a length to chain complex, and we denote its tanagraph by this T of C. And so how to do a lift? Well, we start with a code, and a code with a given parity check matrix. So here we just take a matrix with all 1, and we generate its tanagraph. So here the tanagraph is just the complete bipartite graph. And to generate a covering of this tanagraph, we take copies of this graph, and then we start permuting the edges. For instance, here the 2 leftmost edges have been permuted. You can do this everywhere. And you get a covering space, and there's also this covering map P that projects copies of edges to edges and copies of nodes to nodes. And then it turns out that this new graph is the tanagraph of a code, C prime. And this C prime is what we call our lifted code. And then there's a relation between C prime and C, which is a certain chain map. If we do it for, so here it was a degree 2 lift, but we could do a degree T lift, and we would obtain a matrix like that, which has Pij or T by T permutation matrices. And it's very nice to create LDPC codes, first of all, because the weight of the parity check matrix is unchanged. And it's flexible because we can have integer codes of length integer multiple of these original codes. And for the dimension, we have a lower bound. But for the distance, it's a bit tricky. And in general, people just do a computer search, and then they simulate their codes against some noise and with a decoder. Okay, so let's try to extend this idea of lift to CSS codes. And okay, in this work, in this talk, our setting is that a code is a length 3 complex built from two classical codes which have this orthogonality property. And the tanograph of a classical of a quantum code is just the union of the tanograph of the two classical codes CX and CZ. So here is an example of the tanograph of the Stein code with x, z vertices as squares and qubits as black dots. Okay, and so we can interpret this CSS condition as a graphical constraint on the graph. So there must be an even number of qubit vertices between any x and z vertices. So any x and z, they share an even number of adjacent black qubit vertex. Okay, so let's try to apply naively this lift to a code, so the Stein code. So this is a valid covering of the tanograph, but if you look closely now, these z and x checks, they are adjacent to an odd number of common qubits. So, so it turns out that doing naively, in general, will not give you the tanograph of a code. It will give you some graph which you cannot interpret as a tanograph. And so to solve for this problem, we will consider another object called the Tanner-Cohn complex. And the role of this complex is to enforce the number of adjacent Q vertices between any X and Z vertices to be conserved under the lift, under any lift, in fact. And this Tanner-Cohn complex is a 2D simplicial complex that you build from the tanograph. So you start here from the tanograph of the code, so this graph I just mentioned. And you add some blue edges and faces in the following way. So we will look at an example because it's easier to describe. So let's look at the Stein code again. So this is this K is so it's built first of all by adding an edge between any X and Z if they share some qubits. So for instance, this X and Z, they share 4 qubits, so we put a blue edge between them. And then for each of the qubits in the intersection of their support, we add a triangular face. So here they share 4 qubits, but I only show 2 blue faces. Yes, I will need to put 4 blue faces, but here, so we have 2 qubits here, and and you put this blue face that has for boundary this blue edge here. Okay, let's look at another example. So this is the toric code, and here we have this D check, which has some overlapping qubit with these 4 X checks. So we will add some blue edges between them and faces like that. And if you do it on every pairs of X and Z, then what you recover really is a triangulation of the torus. So you see that it's a very natural thing to do. And now we can reinterpret this CSS condition in terms of this complex, that here this, the HX HG transpose equal to 0 is really equivalent to the following. So every blue edge is connected to an even number of blue faces. And this turns out to be really important for the following. Because now we want to try to do a covering of this Tanner-Cohn complex. So we start from any quantum code Q, and here we create this Tanner-Cohn complex, and we have lots of these blue edges and faces like that, and then we generate some covering. So here I describe it's just some picture of any covering that you might want to create. And it turns out by a property, just a basic property of covering spaces, in the covering space, the degree, so the number of faces to which any edge is connected is conserved, because a covering really conserves the local property of the space you begin with. So here, this blue edge, really, its inverse image by this covering map is a disjoint union of 4 blue edges, each of which is connected to the same number of blue faces. And that's how we know that this complex describes is the Tanner-Cohn complex of some quantum code. And we can easily recover this quantum code Q prime, and this is what we call our lifted quantum code. And again, we have some chain map that relates Q prime and Q. Okay, so to summarize, it's really exactly the same diagram as we had before, only now the classical code has been replaced by a quantum code, and the Tanner graph has been replaced by this Tanner-Cohn complex. And other than that, it's exactly the same procedure. Okay, and it's interesting to create some LDPC codes, first of all, because the weight of the parity check matrices are unchanged. And for the parameters, if we do a degree T-leaf, we know that we have this lower bound on the dimension, but for the distance, it's really difficult to determine in general. So we will look at specific examples. So now, what about the existence of lifts for quantum codes? For this, we have to rely on this following theorem that is a very classical theorem in covering spaces. And it is called the Galois correspondence, which tells you that the degree T connected cover of a space K are in one-to-one correspondence with the index T subgroups of the fundamental group of the space. And you can think of the fundamental group as the group of loops that you can draw on this space, with the group operation being the concatenation of loops. This is enough here for this talk. And for instance, this theorem tells you that some codes cannot be lifted if their fundamental group is trivial. And in fact, this holds for Steen's code and Shor's code, that the fundamental group of their Tanner-Cohn complex is trivial. So there is not a lift in this sense. But if we have the existence of lifts, then there is a combinatorial construction that helps you create this covering. So we will be able to create some explicit examples. Okay, but first let's try to apply this idea to recover some known codes. So if I take now a product of 2 linear codes, so this is the Tilly-Gemort hypergraph product code construction, then as an output code, well, this Galois correspondence, first of all, gives me a classification for free by subgroups of products of 2 free groups. And this is because the fundamental group of the Tanner-Cohn complex of this code is really this product. And also, as an example, which is really the main interest for lifting hypergraph product, you can recover the asymptotically good family of Panteleiev and Kalashov. Okay, let's look at another example. If you input this Z6 times Z6 BB code, well, you can generate all the 512 degree 2 lifts of this code, and you can find 6 possible lifts of lifted codes which have parameter 144, 12, 12, so the parameters of the gross code. Okay, so this is just to show you that the lift is, in fact, familiar to you, even if you don't know it. And okay, and for the main contribution now, I will tell you about some new code constructions. And for this, our approach will be the following. We will rely on this Galois correspondence, which I recall tells you that the degree T connected cover of a space are in one-to-one correspondence with the index T subgroups of the fundamental group of this space. And our approach is the following. So we will start by choosing a certain group, G, that we like because it has many subgroups. And we will find a quantum code such that the fundamental group of the Tanner-Cohn complex of this code is equal to this chosen group, G. And by this Galois correspondence, we know that there exist some lifts because we have chosen this group to have many subgroups. And so we will generate covering spaces of the Tanner-Cohn complex, which means we will create lifts of Q. And then we will compute an upper bound for the distance using the algorithm QDisround of Leonid Priatko. So our first example is, the following exercise. We will find a code Q such that the fundamental group of its Tanner-Cohn complex is equal to this group L of A, which has two generators, X and Y, such that X to the A and this relation is X to the A equals Y to the A. So it's a one-relator group, one of the simplest group you can think of. So let's look at the case L of 3. So this is a space which has L3 for fundamental group. So here you can imagine that there is a polygonal face in between. And 3 is because we have 3 identification on the top and 3 identification of edges on the bottom. And to create a code, we will first make a cellulation. We'll subdivide this big face in the middle, and we will interpret the qubits and we'll interpret the vertices as the qubits and X and Z checks in the following manner. And when we do this, we obtain a quantum code Q, which is a product code locally, but which is not a product code globally. So this is a new type of code. And if we continue by generating the faces of the Tanner-Cohn complex, then we just recover a space which has pi1, which has L3 for fundamental group, because the fundamental group is really a topological invariant. Okay, so we have our code. So let's try to generate some lifts. And here we start with the integer A. So here which is A to be 3, and we get this code which has 16 physical qubits, but it has no logical qubits. And if we do a degree 27 lift, then we obtain a code with a positive dimension and a non-trivial distance. And this code also comes with an automorphism of this group, Z9 summadari product with D3. And if we choose another integer A, we start from this code, which has parameter 20 to 2, and generating a lift of degree 32, for instance, we can generate a code which has positive, again, dimension and distance. So here we really see that the lift has been able to increase both the dimension and the distance of the code without changing the weight of the parity check matrix. Okay, so let's do a second exercise. So we'll find the code Q such that the fundamental group of its Tanner-Cohn complex is equal to this group JAB, which has A generators, and every generator to the power B are equal. So these are our A minus 1 relations. So we have A minus 1 relation of this type. So this is an example for A equals B equals to 3. And here we have this space which has A can be thought of the number of spokes. So here this is we have 3 spokes you can see here. Or you can also think as the number of colors. And B is the number of edge identifications per spoke. So here we have 3 identifications, for instance, of the black arrow. We have these 3 black arrows that represent the same edge. Okay, and we have done this cellulation, and again we obtain a code which is locally a product code. It has the same structure as a lifted product or a hypergraph product, but globally it is different. And we can generate some lifts. So starting with A equals B equals 3, we have a code of parameters 12 to 2, and it has check weight 5. So now, if we generate a lift of degree 27, we can obtain a code which has n equals 18 squared and dimension 4 and distance 18. So we can see that the lift allowed us to get into this new parameter regime where we have the same distance as a toric code, so it's just like the square root of the length, but we have 2 more logical qubits at the price of increasing the check weight by 1. And we can play with other integers a and b. For instance, here we have this code of parameters 1432, and then by lifting, we get a code with increased dimension and distance again. And I should emphasize that this column here, where you see these groups, it represents a subgroup of the automorphism group of the code, which is really given for free by the theory of covering spaces. And okay, so to summarize, we have seen that the lift is a very natural operation to produce large LDPC codes from short ones, and it's really only an extension of the lift of linear codes. And we have been able to create, to generate some known codes that enter into this class. But also, we have been able to create some new LDPC codes, like such as this one with these parameters. And now, yes, I would like to ask you the following question: like, which input quantum code can be lifted to find new interesting family of CSS codes? And I hope this talk made you want to explore in this direction, because this is probably a good direction to create some new CSS codes. And finally, I would like to mention this new work called Moderate Length Lifted Quantum Tanner Codes. And using a similar ID, we've been able to create some new short LDPC codes with distance greater than the square root of n. And this is a joint work with Virgile Guemard from the University of Bordeaux. Okay, and with that, I would like to thank you and questions.
Suppose I start with a longer chain complex where I have some meta checks for the CSS code.
Yeah.
Can your construction be generalized to sort of carry and have some self-correcting code?
Yeah. So in fact, you can do the following. So you can think of every length 3 chain complex in your bigger chain complex as a code. And so you can just do the same procedure that you would add some edges if the extra generators share some basis cells, some basis vector. You would add some edge. Maybe you can change the color, and you would add some triangular faces for every cells in the intersection of their support. So you can really create also a bigger 2-dimensional complex. You don't have to go higher dimension. This dimension 2 is enough, but you can really add some other edges and some other faces in this way, and you would be able also to lift.
Complex, is there any condition on like fundamental group matching or not?
So of course, this Galois correspondence, you cannot go around it. It's really a fundamental theorem, and so you would have to have this larger Tanner-Cohn complex to have non-trivial fundamental group if you want to lift. So yes, by adding some new faces and edges, you might kill the fundamental group even more. So this might be harder to lift in the end.
Hi, thanks for a nice talk. I'm wondering whether your construction has anything to say about, the resulting codes have some other nice properties other than, good coding rates, maybe like they support some transversal gate operations or like, other things you can infer from
So I think it's a really interesting direction to study, and I believe that you can use the local structure of your base code to infer certain properties of the lifted code. You can think about also decoding algorithm that rely on this local structure, or as you said, the existence of fault-tolerant gates. Though this is unexplored at the moment, but I think it's a really interesting direction of study. Yeah.
You use KD squared divided by D as a metric,
Yeah.
K times D squared. Is that suggesting your code has 2D structure?
Sorry.
Does that you want to suggest your code has some 2D structure? Because
Okay, yes, I was just trying to, yes, I didn't explain, but it's just like, for me, the general metric to compare this small, short-length LDPC code is really, the metric is really the parameters of the toric code, because they are very good already. So yeah, that's why I put this indicator, but it was just like for your information. Yeah.
thank you.
Friedman and Hastings was interesting because they figured out like when a code can become geometrically local, right? They like were able to like lift it in some different way to get like a geometrically local code out of a QLDPC code. Is there anything you can say about obtaining geometric locality, or are you just motivated by their construction because they were lifting manifolds, doing coverings of manifolds?
Okay. So first of all, yeah, I should mention, because it's interesting that this whole project started because of this paper of Friedman and Hastings, because at first I was doing the mapping to a manifold and then the covering of this manifold to create some new code. And it turns out that this Tanner-Cohn complex, you can really think of it as the two skeleton of the Friedman-Hastings manifold. It's really the same structure, but they need some other constraint. They need to take care of certain difficulties. But here is really the simplest case of two skeleton of Friedman-Hastings manifold. And I think also that, yeah, this structure could be utilized to think about local, maybe by some subdivision you can create a geometrically local code, and I think it has been also worked out in a paper by Lin. But here I was not really thinking about this aspect of.
Last question.
Can we create a new LDPC code by lifting non-LDPC CSS code?
Can you create LDPC by lifting?
Lifting like non-LDPC CSS code.
Well, it depends what you mean by. Okay, so if you start with one given code which has a check weight, so it has a given check weight. Then if you do what we call a tower of covering, if this exists for your code, then you will obtain a family of code with constant check weight, because the weight is unchanged. So it means that you have a family of constant weight codes.
Thank you.
But maybe this constant is very large because you start with a non-optimal constant check weight.
Thank you.
Okay, let us thank the speaker.